Happy New Year's to everybody. Welcome back to the shop. I hope this is going to be a good year. I think so. But for this video, working with these tension pulley turned out to be one of the biggest rabbit holes I've ever gone down. Learning about bearings and usages and stuff. So for this video, I thought I would show a few different types of bearings, the pros, the cons, the things that you need to know that I've figured out or learned in designing or using different bearings. So I hope this video really becomes something that helps a lot of people out. I kind of wish Pierre's workshop was back. He's another one that threw in the towel. But I'm sure he could have really contributed a lot towards bearings and information about them. So, hope you enjoy. See you next time. There are a lot of different types of bearings. There's roller bearings, thrust bearings, tapered bearings, self-aligning bearings. The list goes on and on. I'm not going to cover all of them, but I'm going to cover the best I can, the most common types of bearings that you probably need to know about for a specific application or job you may be coming up with. These I'll start with. These are called roller bearings. Some companies call them roller ball bearings, but the majority, they're simply roller bearings. Okay, so one of your roller bearings in your bench grinder went out, it's making a lot of terrible noise. You pulled it out. How do you identify it? It's simple. Just about every bearing I've ever seen, the part number is either laser etched into it or it's stamped into it. And they usually don't stamp, because if it's not done correctly, you can damage the bearing itself. Now these are small, so you might not be able to see the part number, but this one you probably can, maybe. Yeah, it's up here. These guys, it's in here, sometimes it's in the seal, sometimes it's on the outside. Flip it over, it's someplace. Yeah, this bearing came from a salvage store. My daughter picked it up for me. Turns out this is part of the landing gear of a 747, which is no longer in service. So yeah, you can pick it up for nothing. So that was cool. Thank you, my daughter. Okay, so now you know the part number. Google it, eBay it, Amazon it. It'll show up. And so now you know the size. Some of them, since everything now is from China, some of them simply say on Amazon 8x 22x4. What that means is the first digit, 8 is the bore, 22, the second one is the outside diameter, and the 4, the last digit, is the thickness of the bearing. Okay, now bearings come, with different seals. This obviously is open. Contamination can get in there and mess it up. This is a steel or some kind of a metal. They change it all. Sometimes it's steel, sometimes it's stainless, whatever. This is a pretty good seal on it. Some of them have just a rubber or plastic seal. And these aren't too hot. Well, these are from China. Some of them I've picked up are really good seals. They're towards the edge in the center. This particular one is pretty bad. You can see a gap. You can get a little jeweler's screwdriver in there and pop it out so you can inspect the bearing inside of it. Okay, so now what are the different parts to a roller bearing? It's very simple. Outer race, inner race. The races have grooves in them, which the ball bearings ride in. And then after the bearings are put in here, they'll press in what's called a cage. And the function of the cage is to keep all of the bearings equally spaced so that there's no play in the outer race or to the inner race. So that's the purpose of the cage. Next up, the loads. I find axial and radial loads very user-unfriendly terms, so I have a little chart. You'll probably catch me switching them or getting them wrong. Axial loads are this way, the force that goes this way. Radial load is the force that goes this way. Roller bearings are designed to handle radial loads. They do not like axial loads. You will damage it. So you have to do something to keep the radial or axial load off this bearing, just radial only. Now, how does it get damaged? Boy, this is pretty easy to explain. Alright, I mentioned there's a groove in there, and the cage keeps everything separated. So you have a ball bearing, and it's riding in a groove, and the cage is on top of it, keeping it separate, keeping it in position. So what happens is when you put the side load on it, this bearing wants to walk up this groove edge here. The more it walks up, it starts bending the cage. As the cage bends, it allows it to walk up further. And then what happens is the bearings are no longer held equally spaced. And when that happens, the outer race now can start moving away, which allows the bearings to move further, which bends the cage further, and the next thing you know, the bearing can rock like crazy. So that's how the damage works. How do they assemble them? Really easy, because I just kind of explained the movement of them. If you take all the bearings and you move them down here, there's nothing keeping the top of the outer race from coming over here. So when you drop it down, giant gap here. All the bearings can drop in. You move them back to a position where they're equally spaced, keeping the outer race the same distance every place from the inner race. Then you press the cage in there. So that's how they're damaged. You want to look at the quality of a bearing? Pretty easy. It's all in the cage. This particular one is US made. This is China made. Same way with this one. This one, when you look at the cage on it, it can't move to the side. It fills this space up really good, and the top of the cage is on the center of the ball bearing. These guys, if you get one from China that's open or whatever, you can easily get a screwdriver down in there and you can pop this off. I can't see the gap. There, done. If you look at the cage in this one, this is really prone bad to axial loads. It can take the radial, but not the axial. Why? This cage can move a lot. And the cage doesn't cover the entire ball bearing. So what happens is when you put an axial load on this guy, that cage is going to move down, which allows the ball bearing to move a lot and really bend it. So this guy gets destroyed real fast. This one, no. Cage can't move, and it's on the center. It almost completely covers the ball bearing. This one, only maybe half or 3/4 of the ball bearing. So that's what you look for when you're looking for the quality of a roller bearing. So I think that's about all I can say on these guys. Okay, with respect to roller bearings, let me talk about quality or precision, whatever you want to call it. As far as quality, you can look, I bought a pack of 10 of these off Amazon. They're from China, and I know it because there's no manufacturer on it. Each one of these does have a part number. This one's very small, but I think it's worn out. There's no manufacturer on this one. This one I said was earlier was from China. I don't think so. This is it's got the part number very clearly laser etched on it and the manufacturer. This one only has the part number in the seal. This is plastic. Some of them are rubber, but looking at the finish here, this thing is obviously ground. I know if you've looked at some other tooling, angle blocks and things, you can see that the particular surface pattern where it's been ground. These two are like a mirror. They are, I don't know how they do it, whether they lap them or what, but they're a beautiful finish. They look like a mirror, like glass or whatever. Very smooth feeling. These are somewhat smooth, but not as smooth as these. But that would tell you the quality of a bearing, whether it's, you know, got a nice outside race or it's been just ground. And I was surprised too. I used my Mitutoyo digital caliper, micrometer, and I measured every one of the 10, and they came into 0.62965. Exactly the same on every one of them. So I don't know how they held that tolerance to a half, a tenth of a thousandth. They were perfect. So that's one thing to look for in quality. The other thing is you don't know what you're going to get. Typically on Amazon, they'll say, okay, it's a 8mm bore, 20mm OD, and it's 4mm thick. You don't know what you're getting until you get it. If there's a manufacturer name listed, you can go look it up, and then you'll know. Like this said it was a 22mm OD. It is not. It's undersized. So this is a slip fit, like say into a pulley. And then the center is also undersized. It's at 8mm, it's under. This is a press fit onto the shaft and a slip fit into the pulley. And that's why they have to hold these ridiculous tolerances, because if you made 20 pulleys and the holes in them are all 22mm exactly, you don't want one of these to be oversized and not go in, because it would be trash on the production line. So I have yet to understand the difference, or why for one particular situation you would want to press the outside race into the pulley and let the shaft slide, or why you would press this onto the shaft and let the outside slide. To me, pulleys and things, I want it pressed into the pulley and I want it to slide on the shaft, because I don't want to wear out the pulley, you know. This is not going to wear out any shaft. Shafts are usually super hardened things. So that's just the tolerances. And, you know, again, if you know the manufacturer, you can go and look it up on their website, and you'll know what's the size, actual size, whether it's oversized or undersized. These, I wanted the bore to be oversized, and that's what this is. This slides. I think I just said it was under, but this one I bought, and turns out the bore is oversized, so it slides on the 8mm shaft. The outside I pressed in. So, but again, you don't know what you're going to get. One more thing I want to cover on this type of roller bearing is pay attention to the chamfer that's in here. I'm not sure if I can really show it or angle it, but there's a serious chamfer in this guy. In other words, this is not a square edge. So, benefits to that is if this is going to get press fit on a shaft, the chamfer helps you keep it straight and gets it to go on the shaft. The bad thing is if it's not press fit on a shaft and it's just floating, this chamfer creates such a force that if it's retained by a snap ring, the snap ring will come off. So if you have a big chamfer, you need to put a washer on this first and then put your snap ring or whatever retaining thing you have on it. So that's one issue. The other issue is I didn't really explain why these guys don't like radial loads. So for that example, let me bring this in, make sure the camera's got it in view. Yeah, I think so. Pretend that is a ball bearing. In this type of roller bearing, the raceway is on top. So you're riding in a groove like that, and the force is this way. So no big deal. If you apply an axial force, what happens is you have 2 points of contact that are trying to keep that bearing in that groove. So what happens is, I'm going to use a big ball bearing because I can't hold the small ones. You're pushing it this way, so it's going to want to walk out on this point right here. Second it lifts up, it bends the cage, and it also starts destroying this corner. Bending, if the force is this way, it's going to start damaging this corner of the raceway. So that's what happens. It lifts up, damages the cage. They're not equally spaced, therefore everything starts rocking on them. So it's just something to pay attention to. If this were a thrust bearing, now you've got the cage this way. And so it loves the force this way, but doesn't like this force. Same situation, 2 points, it's going to start lifting out, start damaging things. So it doesn't like that. Alright, I have no idea, stupid selfie stick, how you can adjust it so the feet aren't in the picture, but another type of bearing is called a thrust bearing. This is a thrust ball bearing type. There's also a needle thrust bearing type. So, all kinds of things to these guys to talk about. First up, this is called a single direction thrust bearing. And what does single direction mean? It's simple. It has nothing to do with the direction of rotation. It can go either way. What it means is single direction means the axial load can only be one way. And as far as I can tell, I mean, none of them actually say both directions. I have a feeling the thrust needle bearings allow axial loads in both directions, but all of them that I've seen that say single direction, you'll see this side's an open kind of cage, this side is sealed. What they want is the open side is the load side. So say the pencil is a pulley, and the pulley wants to do this number on the shaft. So you're going to put the open side towards the pulley. So it's going to press on that side, and it can take that single direction. It doesn't like the other direction. Why? I don't know. The other unique thing about these is there's the 2 races with the grooves in it that the ball bearings ride in. One of them is going to be undersized. This is supposed to be 8 millimeters. I don't know which one's which. This is probably the undersized one. And when this just goes on the shaft, it just fits the 8 millimeter shaft, and it keeps this guy from moving this way because they don't like the radial load. So this goes next to the pulley first, then this bore is oversized so it can move around, but it's going to stay centered on the shaft with respect to the ball bearings. For these to work on a standard roller bearing, it's absolutely flush, meaning the outer shaft, the outer race and the inner race have the same thickness. So you would put this guy against it, and you want it, how do we explain it? These guys are absolutely flat on the back side. So what's going to happen is you want this to touch the outer race and the inner race, because it's going to keep the inner race from doing this number, turn it sideways, from doing this number with respect to the outer race, because it's going to keep it in position. So smaller diameter goes against the bore, against the bearing. Then this goes, you know, if the pulley is this carpeting here, then this goes that way, and this goes on top of it. I don't see anything saying you grease them, you oil them, anything like that. I imagine you can put grease on them, but no big deal. And I haven't seen any information on the thrust needle bearings, just thrust roller bearings. So that's kind of all I can say really about these guys. Again, you know, every time I see one that's got this open cage looking thing, is a single direction thrust roller bearing. So, and I was curious too when I bought these, it's like, why is one bore undersized compared to the other one? 8mm just fits this thing nice and snug. This walks around. So, again, you know, the smaller bore goes against the load. Needle roller bearings. Boy, I thought this was one of the coolest inventions there was. So yeah, if you look down in there, you can see the little needle bearings in there. They're sort of like barrels that roll. What can I say? Okay, so I thought these would solve a lot of problems. They can take a tremendous amount of load and high RPMs too. So you think about it, if you got a shaft that's turning at 2,000 RPM, boy, these little bearings are booking it. They say don't use grease, just light lubricating oil. But in any case, these are 8mm, and I needed to make a shaft for it because I'm going to put it on a pulley about that far apart, I guess they were. So bring out the gauge pins. 8mm is 0.315, goes in there easily. Sloppy. 317 goes in there. 318 was a nice fit, pretty tight. But for some reason, the gauge pin would lock up in there. I mean, you'd spin it and push it, and boom, all of a sudden it's just jammed. It's seized in there, and you had to fiddle around for a bit to get the gauge pin back out. So I'm looking at the cage that's down in there, and it doesn't really keep the needles centered. So I'm thinking, all right, their needles are just jamming to the side. Ignoring the problem, I made the shaft, 0.318, pressed these into the pulley, put it in service, no problem. A couple of days later, examining the shaft, these guys ate a big chunk out of the shaft. Where the needles were, there was a big missing section. Where the steel went, this was an 1144 shaft, which is pretty tough. So the outside of the pulley really ate into the shaft. The back slightly ate into the shaft. Took me a long time and a lot of research to figuring out what happened. Why did it do this? I mean, I know they don't like axial loads, but they can take heavy radial loads. So I had put a thrust bearing on the front of it. These guys were sliding on the shaft, so there is no axial problem here. Why did they seize up, or what happened? Why did it wear a groove? Turns out I found a manufacturer talking about it, and the guy said, yeah, the problem is if you're not equally loaded on both sides of the needle, it's going to skew. So that's what happened, is I'm sure the loads were off balance, the thing skewed, so it wasn't really rolling, it was more like skidding on the shaft. The other thing is, I think these things are pretty unforgiving in the sense that if you're not in alignment, suppose you're a little bit cocked, that's a lot for this picture, but guess what? You're putting a tremendous load here and out here. Well, I don't know whether that's going to cause the problem too. You know, essentially, can't even talk today. These at an angle, I don't know, a few thou or something like that. Are they rolling or are they skidding or what? So, and do the loads change? Especially if you're out of alignment this way, I don't know what's going to happen here. So I have a feeling that's what happened here with these guys. So in any case, these are very difficult and I think unforgiving bearings to use. So I just wanted to do one kind of visual aid that I thought of that can help you understand what's going on. Suppose my finger is the shaft. It's round. I have a needle bearing here, and I have a needle bearing here. Looking down in the needle bearings, they're pretty far apart. So from the peak, you got to remember there's a peak to this, and there's two needle bearings sitting here. Now, if I take the body to it and I tilt it, this is going down, applying more pressure here. This is coming up, applying more pressure here. So what's going to happen is when this comes up, it's going to make the bearings separate. So look, they're skewed. They're not rolling anymore. So on this guy, when you tilt it, the two needle bearings are going to split here. The bottom's coming up. These are going to split. But because there's more gap down here and they're cylindrical, they can actually do that number. You know, they're parallel and they're going to do this number. So they're not going to be rolling. They're going to be skidding, slipping. I don't know how much tilt. I have a feeling that you've got to be better than 1/10 of a thou, because the slightest bit of angle, they're going to want to skew. Another type of bearing, which I can't find small, is the tapered roller bearing. And you can see there's an angle to them. So these things take radial and axial loads without a problem. I had bought these a long time ago because everybody was replacing the traditional roller ball bearings in the headstock of a mini lathe with these, stating that it improved their quality. I don't see any problems so far, but in any case, I did see the part number on the mini lathe, ordered them, so these should press fit in. You really got to tear it apart according to the videos to get it in there, but yeah, these should make an improvement to it. But again, I cannot find these in an 8mm bore. Wish I could. Maybe it's out there, maybe not. Maybe it might be a manufacturing problem. But in any case, there's your last bearing maybe I'm going to review, and then I'll get into some of the theories here coming up. But alright, move this camera over a little more. Yeah. Alright, first, by no means, I am no expert at all on bearings. Everything I'm about to talk about is from my own thinking, conclusions, talking to bearing manufacturers, and watching a bunch of YouTube videos on the subject. So, if you can leave a comment that it got something wrong or you're adding something, by all means, please leave a comment. Okay, let's say this is a pulley. You've got a pulley and you're going to put it on a shaft. What are you going to do? Well, you can always press in a bushing. You can use brass, bronze, copper, and there's self-lubricating bushings that you can buy. Go and research those. I forgot the particular name to it. For something like this, you're obviously going to press fit this into your pulley, and it's just going to ride on the shaft. So now you need to make sure you have something that keeps this pulley from doing this number. So you're probably going to put a thrust bearing on each side. This will handle the axial load, and you're going to put thrust bearings so you don't care about the radial load. because it's going to slide on the shaft anyway. One option. Second option, let's do needle bearings. Let's say you're going to use one bearing in the middle of the pulley. You have the same kind of issue here. When you bore this out, you got to make sure your headstock is not tilted, or you're going to be boring a funnel for a hole. You got to make sure your compound, if you're using that to bore the hole out, is perpendicular, or whatever you want to call it. It's not making a funnel for a hole, or your press fit isn't going to be too good. This type, needle roller bearings, you're definitely going to press fit this into the pulley, and it's just going to free play on the shaft. But with these, I've already said, if you have more load on one side than the other, they're going to skew. So you have to make sure this guy doesn't do this number or this number. So you need a thrust bearing on both sides if you're going to use that. These, if you're going to use two of them, now you have more issues, because now you have an alignment issue this way, you have alignment issues tilting it, all kinds of different things. So these are very tough, in my opinion, and through my experience, to work with. The taper bearing, I put it away, but the taper bearing is not going to allow for this kind of a problem. You know, if your shaft is at an angle, you're going to have some issues with that. So you just need to think about what you're doing with the taper bearing. These are probably the most forgiving, because again, the balls bearings are riding in a groove in the outer race and the inner race. So if this bearing tilts slightly, who cares? It's still riding in the groove. Same way if it tilts this way, yeah, they're still riding in the groove. So this is probably the best design for a single bearing. Double bearings, you got to make sure you're in alignment this way or this way, whatever. And the tilt, again, doesn't really matter. And for these, then it's a question, do you press them on the shaft or do you press them in the pulley? Something you just really need to start thinking about in your design or your application. So there you go. It's different types of bearings, their pros, their cons, and so on. So I hope this video helps somebody out.